Welcome to this Birkbeck Inspires session about future sea level rise and climate change. My name is Becky Briant. I'm in the Department of Geography in Birkbeck in the University of London. And this term I've been teaching on our Masters in Climate Change. I've been teaching about 45 students about climate change, the science, and also what we can do about it. And sea level rise is a really important part of the climate change story. It's a really significant impact. As you can see here, large numbers of people are living on land that's expected to be under sea level by 2100. But then the question obviously comes, how do we know that these people are expected to be under sea level, and how much is sea level likely to rise? And so this map here assumes a rise in sea levels of 50 to 70 centimetres in response to a 2 degrees C temperature increase. But it's important that these people, that they stated this when drawing this diagram, because it's not entirely clear, well, it's not at all clear whether that is actually how much sea level will rise with a 2 degrees C temperature increase. And bear in mind, we've had about 1 degree of that already, because there's things about the system that we don't yet know, or don't yet know how to model effectively. So we can also show how coastlines might change. This here is with about 1 metre sea level rise, and in the top right hand corner we can see Bangladesh. Obviously that's large parts of that relatively small country that would be underwater by 2100 if there was a 1 metre sea level rise. So there's various reasons why sea level rises when temperatures rise, and they're shown here on this diagram, which is from an IPCC special report released last year. So if you look at the diagrams, they all start in 1950 and go to either 2100 or out to 2300. And they show the changes that have happened with the purple line, the changes that might happen in the future, depending on how many greenhouse gas emissions we continue to make as a globe. And so, first of all, ocean heat content. Now, what happens here is that water, it takes up more volume as temperature rises, and this is a physical property of water, and so we can estimate this fairly effectively. There's obviously a problem in knowing exactly what the average ocean heat content is when different parts of the ocean are at different temperatures, but that's relatively easy to model. The other contributor to sea level rise is melt of glaciers and ice sheets. And you can see here that we've separated out Greenland, Antarctica, and other glaciers. And there's two parts to that, and one of which is easier to model, which is called mass balance, where we just look at the difference between accumulation, so snow, in higher parts of glaciers and ice sheets, and ablation, usually melting, but also icebergs, in lower parts of glaciers and ice sheets. And we can measure that because we can model that because we know how temperatures are likely to change under different scenarios. We are less clear on precipitation, but we have a bit of an idea. However, the reason it's hard to model is that that's not the only thing happening in glaciers and ice sheets, and I'll talk about that more in a minute. Of course, the other uncertainty is we don't know how much emissions we're going to continue to pump into the atmosphere. So we obviously have a lot of international discussions and agreements, and the Paris Agreement that was agreed in 2015. But whether national governments and businesses and individuals will follow through on the commitments that have been made under the Paris Agreement seem equivocal at best. Some of them don't even want to, and some of them say they want to but aren't taking sufficiently radical action. And you can see that sea level in 2100 is quite different. If we go for a low emission scenario in the blue of 0.43 metres, or a higher emission scenario in the red of 0.84 metres. And of course, there's uncertainty around that, as you can see in the lighter coloured shading around the lines. And I should say that at present we're following the red line. So, as I was saying, linear responses, mass balance changes can be modelled, but the problem we have is that ice sheets in particular behave in significantly non-linear fashions. And that's particularly shown in the behaviour of ice streams, which are around the edge of the ice sheet, and they are smaller glaciers within valleys at the edge of the ice sheets, which concentrate the flow outwards of the ice that's accumulating in the middle of the ice sheet. And what we've seen in recent years is that those ice streams, those glaciers around the edge of an ice sheet, are accelerating, and ice is being moved out of the ice sheet faster. And you can see this particularly in Greenland in this diagram here, where the purples and the blues are significant thinning, and the reds and the yellows are where the ice sheet's growing. And you can see that also in West Antarctica, and a little bit also in East Antarctica, which is worrying, because we thought that East Antarctica was more stable than West Antarctica. And you can see that it matters because Greenland, if it melted entirely, would have 7 meters of sea level rise locked up in it. Not by 2100, wouldn't melt that fast, but maybe 3 or 4 centuries out. And we would be, once Greenland had melted, we would be committed to that sea level rise over that time period. We couldn't reverse it. And 58 metres in Antarctica. Most of that's in East Antarctica, which is more stable, but even so, it's a concern. So this just shows you the projections from the IPCC, that's the Intergovernmental Panel on Climate Change. And these should be seen as minimum estimates because they don't include non-linear ice sheet behaviour. And you can see again that there's this difference in emission scenarios, and potentially up to 1 metre as a maximum of sea level rise by 2100 under this highest emission scenario, which, as I say, is the one that we're currently tracking without significant action. Now, of course, we don't live in the middle of the sea. We live in particular places, and the ocean is very complicated. So we experience sea level differently depending on where we are. And this just shows you a few examples. So in these diagrams at the top and the bottom, the red line is global sea level, and the grey is local sea level. And so you can see that in Stockholm, local sea level actually goes down because it was covered in an ice sheet in the past, and so the land is still rebounding, so sea level is going down. In Charlottetown, actually this was near an ice sheet, but it was just outside the range of the ice sheet, and it was in an area called Forebulge, which is now subsiding, and so sea level rise is reinforced by subsidence. In San Francisco and Antofagasta, you can't see a trend in sea level rise because there's too much fault movement, and that is overriding the global sea level trend. In Manila, local sea level is rising a lot faster because it's exacerbated by groundwater pumping. So the land is subsiding because the groundwater is being pumped out. And this is really, really common in a lot of coastal areas which are densely populated, because of course the people living there need water. And then in Pago Pago, in the middle of the Pacific, we can see cycles because El Nino doesn't just change temperatures, it also changes the elevation of the sea in the Pacific by a significant amount. This can also be seen in relation to extreme sea level events. So one of the ways in which sea level rise really affects people is that it makes storm events more destructive. And you can see in the top left-hand corner that these historical centennial extreme sea level events are due to become more common as sea level rises. So a 1 per century event might happen 1 per year in the future, because sea level is rising, and therefore even the less extreme events would have the same impact on the land. And we can see in these diagrams 2.6 is a low emission scenario and 8.5 is a high emission scenario. If we just look at Europe, you can see that the number of locations where once a century events turn to once a year events by 2100 is much higher in the high emission scenario. And indeed, in the high emission scenario, there are a significant number of places where once in a century events are already recurring annually. So this is obviously a problem, and we need to think about how we might respond to future sea level rises. So governments around the world are looking at the projections and trying to manage the uncertainty to try and decide how to deal with this issue. And indeed, in the UK, we have an organisation, rather a project called UK Climate Projections. These are updated every so often. The most recent one was in 2018, where it's shown that sea level rise will occur for all emission scenarios everywhere in the UK, even those areas that are rebounding, because they're not rebounding that much anymore. And they will affect these changes in extreme water levels. And you can see that storm events have a significant effect. So if you can see in the middle diagram there, that's the Dawlish train line, which often gets taken out by storms, but this was a particularly bad one in 2013. It's just too close to the sea. And the top left-hand corner is the 1953 storm surge in Essex. Obviously, that was very destructive. And we have the Thames Barrier in the middle on the left, which protects central London from extreme events coming from the North Sea. But by 2100, we will have to have increased the protection, because sea level rise means that these extreme events will no longer be within the range of events that the Thames Barrier was designed for. And this is just to show you finally that the Thames Barrier is protecting London and is closing an increased number of times each year. Obviously, there's some particularly stormy years, so 2014, for example, but in general, there's an increased use of the Thames Barrier. So thank you for listening to this Birkbeck Inspires event. We can be sure that sea level will rise due to future climate change, and we can only at the moment model minimum estimates, but even those suggest it may rise by 80 centimetres to a metre by 2100 if we continue to emit greenhouse gases at the high rate that we currently are.